Now, obviously the pre-image, if you look at the definition of the pre-image of the empty set is empty set. That's why my S, so the part 1 is about showing that S is a semi-ring. We have to test the axioms of semi-ring. This is very straightforward business. Empty set will be my semi-ring because of this identity. Also, I observe that pre-image has this identity. Pre-image concept satisfies this identity. The pre-image of a set difference is the set difference of individual pre-images. In fact, every set operation communicates with the pre-image this way. They're completely interchangeable. But I'll actually decided to show you this part of it, in fact. So look at this. If I start with the element on the left-hand side here, which means that by the definition of the pre-image, the f of x belongs to B and f of x doesn't belong to B1, which obviously means that f of x belongs to the set difference B and B1, which by definition of the pre-image means that x belongs to the right-hand side. And each of these things can be reversed backwards. That's why you have the identity like this. Now, remember if you remember the axioms of a semi-ring, we have to show that actually if the set difference of two elements of my semi-ring, and that's the elements of my S semi-ring, the set difference of two elements of a semi-ring can always be represented as a disjoint union of the elements of semi-ring. So if I take the difference of two elements of my semi-ring, which I now can replace with this object, with this one, because B and B1, they by themselves came from the semi-ring L. This set difference can be represented as the disjoint union of elements of the semi-ring L. Now, implicitly, I use now something I mentioned earlier, that the pre-image freely interchangeable with the operations on sets. I prove it for the set difference. It will be the same for the union of sets, so it will be the union of pre-images of each S. Remember C came from the semi-ring L, and B and B1 also come from the semi-ring L. And we're done, right? Again, we took two elements from the semi-ring L. We have to show that this set difference can be represented as a disjoint union of elements of a semi-ring S. Set difference we replace like so. For this set difference, because B and B1 from the semi-ring L, there is a representation by the elements of semi-ring L. Now we interchange the pre-image and the union, and these elements are the elements of semi-ring S. The definition of the S, we left it on the slide above. Yeah, and that finishes the part 1, that the collection of subsets S is a semi-ring. Part 2 is about the sigma additivity and sigma additivity of M. I will do it in one go. Again, it's a very straightforward business. If I have the measure M of the disjoint union of elements of my semi-ring S, remember all of this from a semi-ring S, by the properties of the pre-image, I can interchange this with the union. Here's the exchange of it. So now it's the pre-image of the one single union. This is a definition of the measure. This is just G of the disjoint union. This is a sigma additive measure by assumption, so I can replace it with the sum of the individual measures, and this again can be replaced with the definition of the measure M, and that finishes the sigma additivity. Again, all of this is very simple business, and all of this is based on the fact that pre-image is freely interchangeable with the operational sets. For the set difference, I proved it here. For union, that's what I mean by saying freely interchangeable. The pre-image of the union is the union of individual pre-images, and pre-image of the intersection is the intersection of individual pre-images. Both of these identities can be shown in a similar way I showed this identity, and that's why part 1 and part 2, it's a very easy, straightforward business. Now,